Next presentation is the micro air cycle system.
Good afternoon, everyone. I'm Philip Campbell, electrical engineering major. I have with me Kay McDaniel, Alex Letts. They're also electrical engineering majors. And our project was the micro air cycle system, or MACS for short. So essentially, the goal of the MACS system is to create an alternative air conditioning system that is more efficient and does not use harmful chemicals that conventional air conditioning systems use. So instead of relying on fans and moving fluids, it relies on electrostatic compression. So the basic setup we have is a set of plates that, when a voltage is applied, a potential difference is applied between them, they compress. This results in a heating up of the air trapped between them, and have that drawn off to cool the air back down to whatever the ambient temperature is. When we expand the vanes, then it creates a cooling of the air, and that will then be released out into the environment to cool the surrounding environment. So our major roadblock this semester, and what our main focus was in the thermodynamics of the process. So we had two main problems. The first problem was what's actually happening in our test environment, because our test environment is basically taking the vanes, putting them into a box, and trying to cool down the box. So that was, my main focus was writing a MATLAB simulation that solved the heat equation in 2 dimensions to understand how the dimensions of our box were hurting us or helping us. And so that's the top graph behind me here is showing several different box thicknesses, which would be actually the critical dimension of the box, or the smallest dimension, and showing how those affect the amount of cooling we would see in the best case scenario across the range of frequencies of operation of the vanes. Then the other problem was trying to understand what's actually happening inside the vanes as they compress and the heat is pulled out and as they expand, and then because the air is then at a cooler temperature than the plates, the heat starts dumping back into the air. So that was Alex's main thing this semester, was writing a console model that solved that. So just one image of that is behind us. And so this led us to a couple of design changes for our system that Kane has been working on implementing, where first we switched from a rather large square geometry vane to a same surface area but smaller rectangular vane to try to fight the effects of lateral heat transfer, because with the dimensions of our materials, our heat transfer layers are very thin, on the order of 100, or really 20 to 50 microns. And so the heat transfers laterally very quick, or vertically very quickly through the materials, but not very quickly laterally. So we changed this rectangular geometry so that we could combine that with some other thermodynamic principles, like an active heat exchanger cooled down to several degrees below room temperature to try to pull the heat off. And then the other thing is that we need a much thicker box than we were originally using, or we have no chance of seeing any cooling whatsoever. And that's basically our project. Are there any questions?
So there were a couple of seniors on 2 micro air cycle projects, and you guys told me the other teams were.
Yes, we've actually worked together with them the entire semester. So we're taking more of the theory approach. They've been on the experimental side. So as our results come out, they've made the changes and they've been testing them. So that's, but yes, we have collaborated.
How efficient is this?
We don't have a measure of efficiency yet. Theoretically, the COP of this is about 5 times that of a conventional air conditioning system, so it should be much more efficient. But that also didn't fully take into account all the thermodynamic effects. So we're still working on developing these models to try to figure out how they fit into everything. Hopefully we can continue refining this and adding a couple other things to put everything together. So like I said, I worked on the MATLAB simulation. Alex was working with console, and then Kane was kind of a liaison between our theoretical stuff and the experimental stuff, helping to integrate our ideas into the designs that the senior design team was carrying out.
Simulations, what were you up to?
So what you're seeing there is actually, it's a normalized Delta T. So what I did was I wrote the program and assumed that we had some vane setup where we could achieve some amount of cooling per unit area of the box, so something like 0.1 degree across the entire box. So ignoring any effects of vane cooling or anything, just trying to get an idea of best case, what could happen. And then I took that and normalized it against that delta T. So all the numbers here are actually some factor times the amount of cooling each individual compression produces. And then running across the range of 10 hertz to 100 hertz, showing that as we get to higher frequencies, we get a drastic increase in the amount of cooling we can get from the system.
If I could just make a comment, the work that you're focused on is actually to develop a very efficient cooling process.
Yes.
And you have limited real estate, probably would help to have maybe a flow diagram or some kind of image that might illustrate how your piece can actually move in more practical. Only because you have to kind of spend a fair amount of time trying to explain why it's important. And it is important, it's just it would really help a little bit more. It's not easy getting previous teams to have that challenge.
If you sought out any help from our colleagues in mechanical engineering to get that expertise in this area?
We've talked some different areas. I know both Kate and Alex, I think, have met with you a couple times to talk about it briefly. We've worked with some people from TI as well, and so we've been reaching out to them because every now and then we hit a problem, especially when we got the thermodynamic stuff. We're all EEs, and so we started trying to reach out and figure out who would be able to help us develop our models. And so we've talked, obviously, to you, people from TI. Dr. Hassanpour is on our list of people to talk to, and Dr. Tadasi as well, about some other mechanical things.